In 4.2, we talk about logarithmic functions. So the horizontal line test shows that exponential functions are one-to-one and thus have inverse functions. The equation defining the inverse of a function is found by interchanging x and y in the equation that defines the function. So starting with y equals b to the x and interchanging x and y yields x equals b to the y. To isolate the exponent y, a new notation called logarithmic notation is needed. This notation gives us a way to name the inverse of f of x equals b to the x. The inverse function of the exponential function with base b is called the logarithmic function with base b. So for x greater than 0 and b greater than 0, where b is not equal to 1, y equals log base b of x is equivalent to b to the y equals x. The function f of x equals log base b of x is the logarithmic function with base b. The first equation is in logarithmic form, and the second equation, which is equivalent, is in exponential form. So we want to write each equation in its equivalent exponential form. So 2 equals log base 5x. So log base b x equals y is equivalent to b to the y equals x. So we just want to keep this in our back pocket. So the base of my log is the base of my exponential form. So in this case, the base of my log is 5, and the base of my exponential form will also be 5. The base is raised to y, which is on the opposite side of the equal sign in the logarithmic form. So this will be b squared, or 5 squared. This is equal to x, which is the part that's attached to the log. And that's how you write it in equivalent exponential form. Let's go ahead and try the next one. 3 equals log base b of 64. So the base is b, and so will be my base of my exponential form. It's raised to the y power, which is on the opposite side of the equal sign. So we really have b cubed, and this is equal to 64. Go ahead and pause the video and try the last one for yourself. So my base is 3. It'll be raised to the y power, and that's equal to 7. Now we're going to go in the opposite direction. So we're going to start in exponential, and we're going to go to logarithmic form. So the base of our exponential is the base of our log. So we'll have log base 12. And then the part that's on the opposite side of the equals, it's what gets attached to the log. So log base 12 of x is equal to the power, which is 2. So our equivalent log form is log base 12 of x equals 2. Let's go ahead and try the next one. We'll have log base b, and then the opposite side will give me the 8, and this is equal to the exponent, which is 3. So log base b of 8 is equal to 3. Go ahead and pause the video and try C on your own. So in this case, we have log base e of 9 is equal to y. Now we want to evaluate. So log base 2 of 16. So let's just say this is equal to x, and we're going to write this in its equivalent exponential form. So that would be 2 to the x is equal to 16. So 2 to what power gives 16? 2 to the 4th gives 16, and so x is equal to 4. Or you can say log base 2 of 16 equals 4. Let's go ahead and do the next one. Set it equal to x and write it in its equivalent exponential form. So 7 to the x equals 1 over 49. 7 to what power gives me 1 over 49? Well, 7 to the negative 2 would give me 1 over 49. And so in this case, x equals negative 2. Or you can say that log base 7 of 1 over 49 is equal to negative 2. Go ahead and pause the video and try C and D on your own. So log base 25 of 5 is equal to x. We're just going to go ahead and rewrite it. So 25 to the x is equal to 5. So 25 to what power gives me 5? Well, 25 to the 1/2 power gives me 5. And so x is equal to 1/2, or log base 25 of 5 is equal to 1/2. And the last one. Just go ahead and rewrite this. So 2 to the x is equal to the 5th root of 2. We can rewrite this a little bit. 2 to the x is equal to 2 to the 1/5. And so 2 to the 1/5 will give me 2 to the 1/5. So x is equal to the 1/5 power, or log base 2 of the 5th root of 2 is equal to 1/5. So we have some basic logarithmic properties. Log base b of b is equal to 1 because b raised to the 1st power will give me b. And log base b of 1 is equal to 0 because b to the 0 will give me 1. So let's go ahead and evaluate. Log base 7 of 7. Since the base of the log and the number are the exact same, this is equal to 1. Or you can rewrite it. 7 to what power gives me 7? X has to be 1. Log base 5 of 1 is 0. And that's because 5 to what power gives me 1? That would give you the 0 power. So inverse properties of logarithms. So for b greater than 0 and b is not equal to 1, the logarithm with base b of b raised to a power equals that power. So log base b of b to the x will give us x. B raised to the logarithm with the base b of a number equals that number. So b raised to the log base b of x is equal to x. So it's almost like the bases cancel and you're just left with the exponent or the remaining piece. So log base 4 of 4 to the 5th is just going to give you 5. So it's a piece that's not the same. 6 raised to the log base 6 of 9 will give you 9. Now let's talk about the graphs of logarithmic functions. We're going to graph f of x equals 2 to the x and g of x, which is log base 2 of x, in the same rectangular coordinate system. So in a previous video, I found the graph of f of x equals 2 to the x. So I'm just going to go ahead and copy and paste that down below here. Now we want to do the same thing for g of x. So let's go ahead and plot the first one. We have -3 to the 1/8. We have -2 to the 1/4, -1 to the 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. So let's do the same thing for g of x. So log base 2 of -3. 2 to what power gets me to -3? Can't really figure that one out, so let's not use it. Let's do -2. Log base 2 of -2. 2 to what power gives me -2? I also can't use this one. What about -1? Log base 2 of -1. Two to what power gives me -1? Still not a great answer. So let's go to 0. Log base 2 of 0. 2 to what power gives me 0? We don't have anything yet. 1. Log base 2 of 1. 2 to what power gives me 1? That gives me 0. So we have 1, 0. Let's do 2. Log base 2 of 2. 2 to what power gives me 2? So it's going to be 1. I have the point 2, 1. Let's go ahead and skip down to 4. Log base 2 of 4. 2 to what power gives me 4? Well, that's 2. So we have the point 4, 2. So if we notice something about our coordinates here, when I have the point 0, 1, I have the inverse, which is 1, 0. When I have the point 1, 2, in the inverse, I have 2, 1. So I'm swapping my x and y's. When I have the point 2, 4, I have the point 4, 2. So what we can do is we can swap the x and y's to find our remaining points. So 3, 8 would give me 8, 3. Negative 3, 1/8 will give me 1/8, negative 3. So we have something along these lines. So a log graph and an exponential graph are inverses of each other, and from a previous section, we know that we can just swap the x and y values. So characteristics of logarithmic functions of the form f of x equals log b of x. The domain of f of x equals log base b of x consists of all real numbers 0 to infinity. The range of f of x equals log base b of x consists of all real numbers. And so this was the opposite in the last section. And so that would make sense because they are inverses of each other. They end up swapping. The graphs of all logarithmic functions of the form f of x equals log base b of x pass through the point 1, 0 instead of 0, 1, like last time. So the x-intercept is 1 and there is no y-intercept. If b is greater than 1, then the graph goes up to the right and is an increasing function. And if b is in between 0 and 1, it goes down to the right and is a decreasing function. The graph of f of x equals log base b of x approaches but does not touch the y-axis. The y-axis, or x equals 0, is a vertical asymptote. So table 4.5 in your book has a table that summarizes the transformations of logarithmic functions. So we're using the same ideas we did beforehand. So let's begin by graphing log base 2 of x and use the transformations of this graph to graph the given functions. G of x equals log base 2 of x plus 1, and h of x equals log base 2 of x plus 1. So I'm going to just go ahead and graph log base 2 of x first, which is the graph we just did. And so let's look at g of x first. So in this case, because the 1 is attached to the x, we will be moving left 1 unit. So like at the point 1, 0, we're going to move to 0, 0. At the point 2, 1, we are going to move to the point 1, 1. And at the point 4, 2, we are going to move to the point 3, 2. And so my vertical asymptote is also going to move 1 unit to the left. Now let's go ahead and look at h of x. Now because there's not parentheses around x plus 1, the x is in the log function and the plus 1 is separate. So we will be moving up 1 unit. So from the point 1, 0, we're going to go to 1, 1. From the point 2, 1, we're going to move up to 2, 2. And from the point 4, 2, we're going to move up to 4, 3. So we have the point 1, 1, we have the point 2, 2, and we have the point 4, 3. Now let's go ahead and give the domain and range of each of these functions. So for g of x, my domain starts from -1 and goes to infinity, and my range is all real numbers. For h of x, my domain is from 0 to infinity, and my range is from -infinity to infinity. So the domain of a logarithmic function, in the previous section we learned that the domain of an exponential function of the form f of x equals b to the x includes all real numbers, and its range is a set of positive real numbers. Because the logarithmic function reverses the domain and range of the exponential function, the domain of a logarithmic function of the form f of x equals log base b of x is a set of all positive real numbers. In general, the domain of f of x equals log base b of g of x consists of all x for which g of x is greater than 0. So we don't care about the base, we just care about that inside portion, and it has to be greater than 0. So when we find the domain of log base 4 of x plus 3, all we want to do is we set x plus 3 greater than 0. And so by subtracting 3 from both sides, we get x equals x is greater than -3. So the domain of your function is from -3 to infinity. So the logarithmic function with base 10 is called the common logarithmic function. The percentage of adult height attained by a boy who is x years old can be modeled by f of x equals 29 plus 48.8 log of x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 8? So in this case, x is equal to 8. So we're looking for f of 8. So 29 plus 48.8 log of 8 plus 1. Well, this is 29 plus 48.8 log of 9. And to get the log with a base of 10, your calculator already has that programmed in. So on your TI-83 or 84, your common log, which is log base 10, is just the log button. So putting this all into the calculator, we get about 76. So this is in percentage, so 76% of his adult height. We also have natural logarithms. So the logarithmic function with base e is called the natural logarithmic function. So when the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 ln, or the natural log of x, minus 11.6, models the temperature increase, f of x, in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 50 minutes. So in this case, x is equal to 50. So we want to find f of 50. Well, that's 13.4 ln of 50 minus 11.6. Your TI-83 and 84 has a button labeled ln. So putting this all into the calculator, we get about 41. So 41 degrees after the first 50 minutes.